Okay, hi everyone, and thank you for joining. This is our last recitation of the semester. And the plan today is to review um, a number of problems for our final exam. We'll see how far we'll get. Most likely, we'll mostly focus on the material that was covered in quiz 1 and quiz 2. So propositional logic and so on, and then proofs. Hopefully we'll do a proof about sets as well. Let me just see. I like this comment that it's kind of crazy the semester is almost over. Yeah, it felt really fast. Yeah, it was like the longest semester ever. It's funny because like in the mid-November, I felt like it's Christmas time. I was telling to my wife, like, I think it's time to put the Christmas lights on the house and so on. It was such a long semester. But hey, we are almost there. We're almost there. One more thing left, which is this final exam. So speaking of final exam, let me make a couple of announcements about it. So the final exam will be on Thursday next week. So that's December 10th. And it will be 2 hours from 3:30 p.m. to 5:30 p.m. So unlike quizzes that were, you had a window between whatever it was, like 7:30 and 5 p.m. When you could start it, and then it was 1 hour. We're not going to do this for the final. So the final was scheduled, even before the semester started, and so there's not going to be a sliding window. So you have to show up during this time. Apart from that, it will be very similar to quizzes. So it will also be through Gradescope. You have to upload it and so on. So that will not change, but there will be no sliding window. So 2 hours between 3:30 p.m. and 5:30 p.m. The same for quizzes. We will again have a grace period of half an hour for you to do the submission. So, at 5:30 p.m., you should start submitting it, and then you have until 6 p.m. to submit it. Again, the same as for quizzes. Don't use this time to actually still work on the final. So this is the time that is budgeted for submission and not for working on the final. And then in terms of what can be on the final, anything we cover this semester is a fair game. So, what I suggest for how to go about studying for this, well, at least try to go over all the practice quizzes and all the actual quiz problems that we had this semester. So go back all the way to our chapter 1, chapter 2, and study all the problems there, and move from there all the way to graphs. So if you do that, I think that's already a good start. On top of this, you should try to revisit all the homework questions, and also come to review sessions. So today is our first review session for the final. On Thursday, TAs will continue where we left off today. So they will cover graphs, but also problems related to the final. And then on Monday, there will also be review sessions for the final. So, join all of these. We'll be solving problems that are similar to what you'll see on the final. And so I think that will be a good exercise for you. And then office hours will continue until the final. We still have to make a final announcement about that. Professor Phillips already made one announcement, but I think we'll add actually more hours. So there'll be plenty of office hours between now and the final for you to resolve any issues you might have and problems and so on. And then finally, don't forget about the last homework, which is due this Friday. Okay, so those are the announcements I had. Any questions about these?
Is the index card policy the same as the previous quizzes?
Yes, so index card policy is the same. So you get one sheet of paper for the index card. Good question. Any other questions? Okay. Okay, so let's start our review. By the way, you can also always speak up if you have a question you want to ask. So either write it in the chat or just unmute yourself and speak up as usual. Okay, so let's start with propositional logic, in particular implication. So, of course, you should know truth tables for all the propositional logic operations that we covered. You can write them down in your index card, but I suggest that you actually learn them by heart. They're really useful in many contexts if you look for programming and so on. When you're writing your if conditions, right, and you have or and, those are basically your truth tables there. But I want to visit the application because I think it's particularly tricky for students because it's a little bit kind of weird. So this is how we denote application with an arrow. And then let's make sure switch to red. It'll probably be a little bit easier. The way we read it is, if P, then Q. And we see that a lot in our propositions for proofs as well. Then we covered a bunch of different concepts around application. So negation is P and not Q. Converse is Q implies P. Inverse is not P implies not Q. And contrapositive, that's the one that is particularly important because we use it in proofs, is not Q implies not P. So just as a reminder, contrapositive is equivalent to the original application. So if you write the truth table for contrapositives, you would see that they're equivalent. And why I think that the implication is a little bit confusing, you have to remember this. If hypothesis is false, the implication is still true. And then if we look at the truth table, we can see that the only row where implication is false is if hypothesis is true and the consequence is false. Everything else is true. And then we also have biconditional, which is P is equivalent to Q. So that means that P implies Q and Q implies P. Okay, so that's implication. So make sure to understand implication. And here is the first example problem. I'll give you 1 minute to determine which of these sentences are true and which ones are false. And they're all related to implication, of course. How do we know these are implications? Well, we have this if-then template. So this is P, this whole thing, and this whole thing here is Q. So yeah, so just write down next to all of them whether they're true or false. Okay, so let me go through all of them. So I'll make little notes about the truth value of P and Q, and then we'll determine the truth value of the whole implication. So for the first one, P is equal to true, because 1 plus 1 is equal to 2, and Q is also true. So if you would look at the truth table on the previous slide, you know that if P is true and Q is true, then the whole implication is true as well. So the value of the first one is true. In the second one, P is false. 1 plus 1 is not equal to 3. And Q is true again. And here we have to be careful. False does imply true. So this is true again. Last one, P is false. Q is false. And the value of the whole proposition is again true, because false does imply false. So the only one that would be false would be something like if 1 plus 1 is equal to 2, then 2 plus 2 is equal to 5. So in this case, we would have P is true and Q is false, and that is false. Okay, so this is how implications work. Any questions about this?
Yeah, I don't quite understand the second example, how false leads to true.
It just follows from the definition of implications. So if I go to the previous slide, you can see the truth table of the implications here. And the definition of this operation is that false, if P is false and Q is true, the implication is true. So there is no big magic here. You have to know the truth table, this little thing in the corner for the implication. And based on that, you know what it evaluates into.
Okay, so just follow the table.
Yeah. And of course, I mean, once you kind of practice this and so on, it just comes kind of naturally. Like I don't really think about it that much. I mean, I don't know, it's like a multiplication table. I mean, you don't really think much why like 8 times 8 is 64, right? I mean, you just know it. So the same is with truth tables for propositional logic operations. You know, you just learn them by heart and they kind of sink in, and then you don't really have to kind of think about them or refer to them anymore. But of course, you know, if you're not comfortable with that, you're more than welcome to write them down in your index card. Any other questions? Okay. Let's move along then. So this was a question from quiz 1. And, you know, I think the truth tables are really important. So, you know, make sure to practice and understand truth tables. And, you know, they're not too hard. And yeah, so that's just a little, you know, let's say hint for the final. Okay, so using a truth table, we want to prove this equivalence. And we should explain briefly why the equivalence holds. So how do we do this? Let me sketch down at least the start of the truth table for you. And then I'll give you a couple of minutes to fill it in. So we have to first note down all the variables. So we have P, Q, and R. And then let's do one big line. And sorry about my handwriting. This is going to be a little bit tricky. Not a lot of space. And now we have to note down all possible valuations of these variables. So we have false, 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 true, false, true, false, false, true, 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 false, false, true, false, true, 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 false, true, true, true. Make sure to do this in an organized way. I was kind of starting with the kind of right-hand side, and I was changing R, and then I would change Q, and then I would change P. A good sanity check that you should always do is that you didn't miss any. So if you have 3 variables, you should have 2 to the power of 3 rows. So you should have 8 rows here. So I can count them. 1, 2, 3, 4, 5, 6, 7, 8. Okay, I have 8 rows, so hopefully I didn't miss any, right? So these are good sanity checks to do so that you don't miss any. Okay, so that's the first step. And now for each sub-expressions of this formula here, we have to add them as columns in the truth table. So we have not R. We have P implies Q. We have the whole left-hand side. So P implies Q implies not R. And don't skip any steps here, right? So each sub-expression has to be present in the truth table. Then on the right-hand side, we already have not R. We don't have not Q. By the way, I apologize about the noise in the background. I think there is a guy with a leaf blower. And there's nothing I can do about it, really. P and not Q. Okay. And the whole thing. Not R or P and not Q. Okay. So that's a truth table. I'll give you now maybe 2-3 minutes to fill this in. And then also think about why they're equivalent and write it down. Okay. And again, you can have truth tables for each individual operation in your index card, but I do suggest that you practice this a lot so that you just know them by heart. So yeah, give this a try. Okay. So if you're not completely done, that's fine. I will do, let's say, the first 2 rows for you. I won't go through the whole thing just in the interest of time. But let's see how we will do the first 2 rows. So we have not R. So R is false and not R is true. Then we have P implies Q. So false implies false. That's true. So this all follows from truth tables of these operations, right? Then we have P implies Q implies not R. So P implies Q is true. Not R is also true. And so this is going to be true. Then we have not Q. Q is false, and so not Q is true. P and not Q. So P is false and not Q is true. So we have false and true. That evaluates to false. And then we have not R or P and not Q. So not R is true or P and not Q is false. So we have true or false, which is also equal to true. So that's the first row. Let me do second row as well. Not R is false. P implies Q is again true. P implies Q implies not R. So we have true implies false. That's the one that is false. Don't forget about this. Then we have not Q is true. P and not Q is again false. And then we have not R, which is false, or P and not Q, which is false. So we have false or false, which is again false. And so on. You continue doing that for all 8 rows. And now, how do we know that they're equivalent? We have to compare these 2 columns. So if these 2 columns have the same valuation for every row, then the left-hand side is equivalent to the right-hand side. And you should write that down as a simple sentence. So this is how we do truth tables. It's a very important concept, and so make sure to practice truth tables for the final. Any questions about this? Okay. By the way, this should be, I would consider this to be a very simple question for the final. So this is something that, everybody should solve without any problems in a couple of minutes. Okay, so let's move along. Okay, let's do some proofs. So we covered a couple of different ways of doing direct proof. By cases, by construction, by induction, and then in terms of iterative proofs, we did a proof by contrapositive, where we prove not Q implies not P instead, and by contradiction, where we assume both P and not Q are true, and we follow the proof until we show a contradiction. Okay, and if we're looking for a counterexample, we have to prove that the implication is false. So let's do some of these proofs. So here's the first one. This one is really simple. We want to use proof by contrapositive to show that if 3n plus 2 is odd, then n is odd. So how do you do this proof by contrapositive? Just remind you. So first write down what the contrapositive is of this sentence. And then you try to prove that, right? So I'll give you a couple of minutes to do this. This one is really simple. So you should be able to prove this in 3-4 minutes. And then I'll prove it for you guys, and then we'll take any questions you might have. Okay, so give it a try. Okay, I hope most of you are done. So let's do this. So let's first write down the contrapositive. So the contrapositive of this one, so is if n is even, then 3n plus 2 is even. So that's the contrapositive, and now we have to show that this is true. So how do we do this? We write down what we know. So we know that n is even. So that means that n is equal to 2 times some k, where k is an element of z, of integers. And from this, we have to show that 3n plus 2 is even as well. So then 3n plus 2 is going to be equal to, we plug in this 2k, so we have 3 times 2k plus 2, and that is then equal to, we pull out 2, we get 2 times 3k plus 1, and that is equal to 2 times L. Why can we do this? Because integers are closed closure of plus and multiplication. So because integers are closed under addition multiplication, and k is an integer, we know that 3k plus 1 is also an integer. And so we can substitute L instead of 3k plus 1, where L is an integer. And so we get that 3n plus 2 is equal to 2 times L. And then from the definition of even, it follows that 3n plus 2 is even. And that concludes this proof. Any questions about this proof? Okay. Right, so this is just a simple proof. Again, I would consider this to be an easy problem on the final. You don't have to think of any tricks or something like that. The proof just kind of falls out on its own. So yeah, I would say it's an easy one. Okay, so let's move ahead. Okay, now let's do let's kind of remind ourselves how to do proofs by induction and do one proof by induction. So we use induction when we want to prove statements of the form P of n is true for all positive integers n. Note that in the exam, the same as in quizzes, we will not require from you to figure out what type of proof to use. In real world, if you want to prove some theorem, obviously nobody tells you which type of proof to use. You have to figure out that on your own, and it's kind of a trial and error process. In the case of your exams, to simplify things, we will always give you a hint for which proof to use. So if there is a problem that should be proved by induction in the exam, we'll give you a hint, use proof by induction. So you don't have to think about it. So what's a typical framework for doing proofs by induction? Well, first you have to formulate what the P of n is. What is the predicate you're trying to prove? Then you have to prove the base case. Typically, we have to, base case is proven for P of 1. However, that's not always the case. There is this little note in the bottom. You have to kind of look at the problem statement a little bit to figure out what your base case is. And don't forget about that. And actually, in the example that we'll see, base case is not for 1. It's going to be for a different integer. And then you assume inductive hypothesis. There's 2 ways to do this. You can assume it for p n minus 1, and then in the inductive step you prove pn, or you assume inductive hypothesis for pn, and in inductive step you prove pn plus 1. Both of these work. It's just a matter of kind of personal preference, and sometimes one is easier than the other, and so on. But both of these are totally fine. And then in the inductive step, well, like I said, you either have to prove that P of n is true or that P of n plus 1 is true, depending on what you assume in the inductive hypothesis. Okay, so that's how proof by induction works. So let me see how much time we have, 11:21. So let me do the proof by induction for you. There is kind of a trick that you have to use for this one that is maybe not totally obvious. And then there is a pigeonhole principle that you guys should do. Okay, so you want to show using induction that 2 to the power of n is less than n factorial for every integer greater than or equal to 4. So let's write down our predicate proposition. So P of n is equivalent to 2 of n to the power of n is less than n factorial. We have to do base case now. And here's where we have to be careful. So every integer greater than or equal to 4. So we have to show base case for P of 4. So what do we get? We get 2 to the power of 4 is less than 4 factorial. So that means that, what do we have? 2 to the power of 4, 16, less than 4 times 3 times 2 times 1. So we have 16 less than 24. If I got this right, so base case holds. Now we have hypothesis. So in this case, I'm going to assume that P of n minus 1 holds, meaning that 2 to the power of n minus 1 is less than n minus 1 factorial. Okay, let me move to the next slide so that I have a bit more room. So now we want to do inductive step. So we want to prove that P of n holds using the inductive hypothesis. So how do we go about this? So what is P of n? So we want to show that 2 to the power of n is less than n factorial. And we want to leverage the inductive hypothesis to be able to prove this. And if you remember, I'll write it here in the top right corner. Our inductive hypothesis is that 2 to the power of n minus 1 is less than n minus 1 factorial. So we want to somehow leverage this to be able to prove the inductive step. So we want to, somehow massage this inductive step so we can plug in this inductive hypothesis. And here where this trick, here's where this trick comes into play. So to be able to do this, we pull out 2 here, and we get 2 times 2 to the power of n minus 1 is less than n times n minus 1 factorial. Great. So we're kind of close now. So we have 2 to the power of n minus 1 on the left side. We have n minus 1 factorial on the right side. So that's pretty close to this. But we have this 2 and n here in addition to the inductive hypothesis that are kind of bugging us a little bit. So we should think about, why do we, how can we determine that this, less than holds if we know the hypothesis? So we have to know something about 2 and n to be able to determine this. And given that n is greater than or equal to 4, so we know that n is greater than or equal to 4 from the proposition. So we know that 2 is less than n. We know that that always holds. So given that 2 is less than n, and from this inductive hypothesis, if we plug both of these in here, we know that this left-hand side is less than the right-hand side. So we know that 2 times 2n minus 1 is less than n times n minus 1 factorial. And so we've showed that then 2n is less than n factorial. And that concludes our proof by induction. So the tricky part here, is figuring out basically that 2 is less than n, which helps us to be able to determine this. And that's why, I would say this is a little bit trickier proof by induction. So there isn't a lot of work to derive the proof, but there is this trick that you have to kind of introduce to be able to prove this this inequality. Any questions about this proof by induction? Okay, so I'm kind of trying to rank all the problems so you get a sense for what you can expect on the final. So, I would say this is kind of a harder induction proof because, like I said, there is this trick that you have to plug in. So it doesn't just it's not totally straightforward. And so if you don't realize that there is this trick, you will not be able to derive the proof. So I would say this is a harder proof by induction. Okay, no questions. Well, I hope that means that this is all easy for you guys, which is great. So let's do one more. So let's do one pigeonhole principle problem. So just a quick reminder of the pigeonhole principle. So it says if m times n plus 1 objects are distributed among n containers, there must be some container containing at least n plus 1 objects. So remember, n is the number of containers, m times n plus 1 is the total number of objects. Okay, and so here is the problem. So we have 109 people, and the question is at least how many must be born in the same month, and then you have to come up with the proof for this. So I'll give you a couple of minutes to try to solve this. Let's see how many minutes we have left. So I'll give you 3-4 minutes to try to solve this. And remember, you have the formula is m times n plus 1. has to be equal to the total number of objects, right? And n is the number of containers. Okay. So remember, on the quiz or on the exam, whenever you see a pigeonhole problem, you have to justify, using words and sentences, why it solves a particular problem and how you set it up. So what are the objects, what are the containers, and so on. I won't write all of this down because it's not easy to write fast on this, but in the exam you have to do this. But so let's try to solve this. So this is the formula. So the number of containers is going to be the number of months in a year. So n is going to be equal to 12. And now we are putting these 109 people in these containers. And the question is, at least how many must be born the same month? So it means when we evenly kind of distribute them, how can we distribute the most evenly, and how much the container with the highest number of people is going to have people in it. So okay, so we have n containers, and so m times 12 plus 1 has to be equal to 109. So this is the number of objects. From this, it follows that m is equal to 9. And so there will be a container with m plus 1, which is equal to 10 people in it. So there will be at least 10 people that are born in the same month. So this is how pigeonhole principle helps us to solve this problem. Okay, so any questions about this pigeonhole principle problem? So I would say this is a medium hard problem. So I would say it's an easy pigeonhole problem, but students tend to kind of really struggle with the pigeonhole principle and they find it hard. So I would say this is a medium hard problem for the final. Okay, before we wrap up, any questions about anything? The exam, the problems we covered today.
Maybe like how many questions from each section could we predict? There'll be like 3 about induction or just one?
Oh, no. Yeah, nothing close to 3 from each section. Kind of like 1, 2 problems from each section, depending on how hard they are. I mean, think about it. There's like 7 sections we covered. I mean, if I give you 3 problems from each section, you'll have 20 problems, and that's just
Yeah.
too much for 2 hours. So I think you can expect somewhere between kind of 10 and 15 problems. So kind of 1 to 2 from each section. If the problem, like induction, I would consider that to be, let's say, a longer problem. Usually takes more time. So, you can kind of expect 1 proof by induction. Yeah, this was a good question.
Can you explain this last one a little bit? If there's at least 10 people born in the same month, if there's at least 10 and there's 12 months, wouldn't that put you over the 109 count? Because you go 10 times 12, it's 120.
Well, the question is, the question is, at least how many must be born in the same month? And so if you put people in these 12 buckets, right? There will be at least 1 month with 10 people in them.
Yeah, I understand that part. There'll be 1 month with 10 people, but when the rest of the months have 9 people, so it'd be at least 9 would be born in the same month? Because 10 is like the outlier almost.
Okay, maybe I'm reading at least in a weird way. Maybe this should be cleared up.
Because 10 would be the maximum amount of people born in 1 month, right?
No, the maximum can be 109 because they can all be born the same month. So this is like, yeah, we should phrase this differently. But 10 is not maximum that can be born in the same month, right? The maximum is 109. So there could be this like bizarre case where everybody's born in the same month. So this is asking like, if we distribute it as even as we can, at least how many people will be allowed in 1 month? And the answer to that is 10. So I think this is, I apologize for this. I think it's a little bit of a confusing way to phrase this question. So I should rewrite this. But you should be careful. 10 is definitely not the maximum. The maximum is 109.
Okay, no, that makes sense. Thank you.
Yeah. And this is a great question. Yeah, the phrasing of this problem, I think it's confusing with this, like at least how many in the same month. Yeah. Okay, thank you all. We have to stop now because I have to move to the next recitation. Come to office hours, come to Thursday sessions. There'll be more reviews. Thank you, everyone. Bye.